Welcome. In this video, we start section 5.3, Combinations and the Binomial Theorem. In particular, we look at day 1, Counting with Equivalence Classes. Here's the problem. How many three-element subsets of A, B, C, D, E are there? This is a sets problem. You can see I've listed out a few sets there, but how many are there in general? And there's a great trick for figuring this out. We start by counting permutations, not sets, and then we'll modify our computation for permutations to give us the number of sets. So, consider all permutations of length 3 with entries from A, B, C, D, E. There I've listed them all. How many are there? We could compute this easily as 5 permute 3. Now, 5 permute 3 is 5 times 4 times 3. There's another way to think about that. Remember, 5 permute 3 could be computed 5 factorial over 5 minus 3 factorial, which of course is 5 factorial over 2 factorial, and then everything from 2 down cancels, leaves us with 5 times 4 times 3. So we get 60. There are 60 permutations in total. Let's call two permutations equivalent if they contain the same letters. How many permutations are in each equivalence class? Well, the answer to that is 6. That's 3 factorial, because if I have 3 things, I can permute them in 6 different ways. And for example, up above I've circled the 6 combinations that are made all of the letters A, B, and D. So how many equivalence classes are there? Well, there's 60 total permutations, but then I can put these into classes of 6 each, and so we find that this 60 divided by 6 is 10. There are 10 equivalence classes, but of course, each equivalence class actually corresponds to one particular set. So for example, the 6 elements that are circled up above, those really give me the set A, B, D. All right, so how many 4-element subsets of A, B, C, D, E, F, G, H, I, J are there? So there are 10 elements in that set, and it turns out that I can figure out P of 10, 4, 10 permute 4 divided by 4 factorial, and that is 210. How many 10-element subsets of A through Z are there? P of 26, 10, so 26 permute 10 over 10 factorial, and it turns out that equals 5,311,735. Let me show you one other way I might think about these calculations. On top, this 10 permute 4 over 4 factorial. 10 permute 4 is the same thing as 10 factorial over 10 minus 4 factorial, which is 10 factorial over 6 factorial. So then that thing is divided by 4 factorial. It gives us 10 factorial over 6 factorial 4 factorial. That's one way to think about doing that computation. And then down below, this other one, let's see, that was 26 factorial over 26 minus 10 factorial. That's the permute part, but then all of that is over 10 factorial. So let's see, 26 minus 10 is 16, so this becomes 26 factorial over 10 factorial, 16 factorial. All right, so in general, how many k-element subsets of 1 through n are there? And the answer is the number of permutations of length k divided by the size of each equivalence class. P nk divided by k factorial. That is n factorial over n minus k factorial, all of that divided by k factorial, ends up having kind of a nice form, n factorial over k factorial n minus k factorial. We call this C, n of k. We read this as n choose k. Now, the notation with the big C in front, that's what our book uses primarily, and the author says this because it's easier to type. But more commonly in real mathematics, you see the n over k in parentheses more often. It is the number of ways to choose k things from a set of n choices. Here are some quick examples. How many 5-card hands are possible from a deck of 52 cards? Well, I'm selecting 5 from 52, so that is 52 choose 5, and that's 52 factorial over 5 factorial 47 factorial, and that ends up being 2,598,960. A pizza shop offers 14 toppings. How many 3-topping pizzas are possible? Again, there's 14 items, and I'm just selecting 3 of those 14. So I have 14 choose 3. So that's 14 factorial over 3 factorial 11 factorial, and that ends up being 364. I own 30 books. How many ways can I select 10 books to donate to the library? 30 choose 10, which is 30 factorial over 10 factorial, 20 factorial, and that number ends up equaling 30,045,015. There you go, some quick examples of choosing. 52 choose 5, 14 choose 3, 30 choose 10. Now, you can save yourself some computational work if you notice on your calculator. Basically every scientific calculator will have functions for this choosing. So look and see if you can find on your calculator the permute and choose functions, and you can use those from now on as you do the calculations. I think on the TI-83 you can find functions npr and ncr for n permute r, n choose r under the probability menu. All right, some problems for you to try. How many ways can you place 16 identical checkers on an 8x8 checkerboard? 15 points lie on a circle. How many line segments can you draw connecting the points? And connect all the points with lines. How many triangles are there? That is, triangles with vertices among the 15 points. Pause the video, give these things a try, think about how you use the choose function to get your answer, and then unpause when you are ready to check your work. Okay, let's take a look. How many ways can you place 16 identical checkers on an 8x8 checkerboard? Well, there are 64 places on the checkerboard, so the answer is 64, choose 16. And 64 choose 14, that ends up being a huge number. In fact, it is 488,526,937,079,580. All right, so so these numbers can get very big very quickly. That's just 64 choose 6. That's a lot of ways that you can place 16 checkers on an 8x8 checkerboard. All right, next problem. 15 points on a circle. How many line segments can you draw connecting the points? Basically, this is a choose 2 problem, right? Because to make a line segment, I'm basically choosing 2 points and then make a line segment. I choose 2 points and I make a line segment. So every line segment corresponds to choosing 2 points. So the answer is going to be 15 choose 2. And 15 choose 2 is 105. Now let's say I connect all the points with lines. How many triangles are there? So basically, I'm picking 3 points now out of the 15, because any selection of 3 points will give me a triangle. So that's 15 choose 3, which is 455. Let's talk about circular arrangements. This is a different way in which we look at permutations and then we divide out by a different kind of equivalence class. How many ways can 8 people be arranged around a table? So if the seats are numbered, how many ways are there to be seated? In this case, I'm really distinguishing all the seats. Every seat is unique. And so the solution to this is 8 factorial, the number of permutations of 8 people. But in reality, some seating arrangements are equivalent. So we want to consider any kind of cyclical rotation of these seats to be an equivalent seating arrangement. It's like we don't really care where I sit. What's more important is the relationship among the people who are sitting. when are two permutations equivalent? So in this case, two permutations of people will be equivalent if one is a cyclical rotation of the other. And how many permutations are in each equivalence class? Well, if I have a group of 8 people that are seated, you can see the little diagram down below, I can rotate this thing 8 positions around before I come back to my original configuration. So there are sort of 8 rotations I can do. So there are 8 permutations in each equivalence class. So I imagine the 8 factorial permutations that give me all possible seating, but I'm going to put them into groups of 8 that are all equivalent to each other, the 8 cyclic rotations around the table. So finally, I can answer the question, how many distinguishable seating arrangements are there? And that's done with the fraction, kind of like I had calculated earlier in order to figure out subsets. What I'll do is I'll look at the total number of permutations, of 8 people, but then divide out by the size of each equivalence class. This gives us 8 factorial over 8. Now, 8 factorial over 8 happens to equal 7 factorial. Do you see that? You just cancel the 8's. And that solution is 5,040. There is one other way to think about this problem. Suppose we have these 8 people and they want to go to the table. Person number 1, there he is, I'm circling him. Person number 1 demands that he must sit exactly in that spot. So, okay, he sits down, and then the other people sit in relation to him. And how many ways can the other people sit in relation to the first one? Well, 7 factorial, because now there's no rotation. This one person has demanded that he sit there. So there's another way of thinking about this same problem. One person chooses where they're going to sit, and then everybody else chooses around them. You have the 7 remaining people that can arrange themselves in 7 factorial ways. How many ways to arrange 21 kids in a circle? This is a problem that you can visualize. There's a picture. That is literally 21 kids, but the numbers that we get are astronomical. In this case, 21 factorial divided by 21, which is 20 factorial, about 2.4 quintillion ways that they can arrange themselves. Here's a variation. How many ways to arrange 4 boys and 4 girls around in a circle if they must alternate? Boy, girl, boy, girl, boy, girl. Pause the video for a second right now if you can, and think about how you might work out this answer. And then unpause when you want to see the answer, and I'll show it to you. Okay, go ahead, give it a try. Here is the solution. So in fact, the answer is 4 factorial divided by 4 times 4 factorial. Now the second question is, why is that the answer? What did I think about in order to get that solution? Once again, pause the video, see if you can figure out why is that the answer. Here is how we might come up with that solution. First, arrange the 4 boys in the circle. Now, the 4 boys in a circle have a circular arrangement, so 4 factorial over 4 shows me how I can arrange the boys. Then, place the girls between the boys. Now, it's not a circular arrangement anymore. Those 4 places are distinguishable, so the way to place the girls is 4 factorial. Then by the product rule, we multiply the 2 solutions together, and for what it's worth, I believe that answer is 144. All right, so we've seen a couple great ideas today. The first one is this choose function. How many subsets of size k can I get from a set of size n? So n choose k. The second big idea is equivalent permutations. A lot of times I want to count permutations, but I need to divide out by some kind of equivalence class size. So those are the 2 big ideas, and that's a good place to stop for today.